In today's video, I will show acid-base titration calculations for three different scenarios. Titration is a technique used to determine the concentration of a substance in a sample. However, in this lesson, we will assume the concentration of both the titrant and the analyte are known. Our focus is purely on understanding the calculation process, and we will cover three types of acid-base titrations. So titration involving in strong acid and strong base. In second case, we will use weak acid, but the base will be strong. In the third case, strong acid and weak base. And I will firstly want to mention about a few things about the titration. So we have simply an Erlenmeyer flask. So we have sample in here, and we have a bread. We can put the chemical inside this Erlenmeyer flask by drop. And so simply we use two components, the titrant and the analyte. Normally the concentration of the analyte is unknown, and the Erlenmeyer flask contains the analyte, and the bread contains the titrant. As the titrant is added, we can monitor the pH of the solution by using a pH meter. For instance, we have a pH meter. It is an electronic pH meter, and we can read the pH by using this device. By measuring the pH during for instance, strong acid and strong base titration, we can plot a titration curve. After the volume of added the titrant, we can look at the pH. For this case, our titrant is sodium hydroxide in bread, okay, and we have a HCl as an analyte. As I mentioned, we know the concentration of both sodium hydroxide and the HCl. So for instance, in this case, let's say sodium hydroxide is 0.1 molar and the HCl is 0.1 molar also. If you make the titration at the beginning, for instance, the HCl is 5 milliliter, and the y-axis represents the volume of the sodium hydroxide added, and the unit is milliliter. So at the beginning we don't have sodium hydroxide, so we are at the 0 point, but also pH is very low. It is 1, which is the pH of the 0.1 molar of HCl. When we start to add sodium hydroxide, pH will start to rise, and at some point it started to rise very sharply. And when the stoichiometrically sodium hydroxide and the HCl is equivalent to each other, this point is called as the equivalence point. So the equivalence point in a titration is the moment when the amount of titrant is added is chemically equivalent to their stoichiometric ratios. So we have a 25 milliliter of the HCl, and we have a 25 milliliter of the sodium hydroxide, and their concentrations are same. So in this case we will have equivalence point when the added sodium hydroxide is 25 milliliter. But if we add more, then the pH will start to rise, and in the strong acid-base titration, in this equivalence point, pH will be equal to 7. And if you continue, the pH will be higher than the cell. And we have a nice titration curve. This curve is titration curve, but is also called as a pH curve. So it is completely same thing. So in our case, we are using the 0.1 molar of sodium hydroxide and the 0.1 molar of HCl. And if you want to calculate after addition of 10 milliliter of 0.100 molar sodium hydroxide to 25 milliliter of HCl, what is the pH of the solution? So concentration of the HCl is again 0.1 molar, so it is same concentration with the sodium hydroxide. There is a neutralization reaction, so we have to consider this reaction first. We have a neutralization reaction between the sodium hydroxide and the HCl. So we will form water, definitely, and we will form sodium chloride. So here I want to use mole ratio of both of them, since mole is the most useful thing here. So we have 10 milliliter of sodium hydroxide, and if I multiply it with 0.1 molar, I will obtain 1 millimole of sodium hydroxide. So this is the mole of the sodium hydroxide. But if you want to use the mole, you can definitely multiply it by 10 to the minus 3. So in this case, 1 millimole is equal to 1 times 10 to minus 3 mole. But I will use the millimole, just make the calculations easier in this video. So we have 1 millimole sodium hydroxide, 1 millimole sodium hydroxide, and the HCl concentration is 25 milliliter times 0.1 molar, so it is 2.5 millimole. If these two react with each other, definitely sodium hydroxide is our limiting reagent, which means that sodium hydroxide will be depleted first. So we will deplete all sodium hydroxide, we will deplete the again HCl, which is 1 millimole, and we will create water and sodium chloride. So sodium hydroxide depleted, we have 1.5 millimole HCl, 1 millimole water, and 1 millimole sodium chloride. So HCl is a strong acid, and it definitely ionizes. And if HCl ionizes, it will create hydrogen plus Cl minus ions. And you have to remember that pH is equal to minus log hydrogen plus concentration. And in our case, we have 1.5 millimole HCl, and its concentration is 1.5 millimole over the 35 milliliter, which gives us molarity. So if you calculate this value, 1.5 over 35, it is 0.0428, or maybe I can use 9. So this amount of HCl will be ionized. It completely ionizes, so we will deplete all the HCl. So we will ionize all the HCl and form proton and chlorine ions. So this is definitely molarity. And I can easily calculate the pH since I know the molarity of the proton. So pH will be equals to minus log 0.0429 and should be equal to minus log 0.0429 1.37, and this is the our pH after adding of 10 milliliters of sodium hydroxide. After addition of 25 milliliters of 0.100 molar sodium hydroxide to 25 milliliters of HCl, what is the pH of the solution? So again, we have to use the neutralization reaction. We have HCl and we have sodium hydroxide. In our case, again 25 milliliters times 0.1 molar HCl, and we have 25 milliliters times 0.1 molar sodium hydroxide. So it neutralizes and it creates water and sodium chloride. So again, this is 2.5 millimole and this is 2.5 millimole. And they completely react with each other. There is no limiting reagent. We will deplete both of them. And we will create same amount of water and sodium chloride. So we depleted all the HCl and the sodium hydroxide. In this case, we just have water. And if you remember, ionization constant of water, it is 10 to the minus 14 at 5 Celsius. We are assume that it is in the room temperature. So in this case, hydrogen concentration will be equal to OH minus ion concentration, and it will be equal to 10 to minus 7, and the pH will be equal to minus log 10 to the minus 7, and this is equal to 7. So for the strong acid-base titration at the equivalent point, if both the concentration of acid and the base is same, then the pH becomes 7. But what if we exceed the equivalent point? Then after addition of 35 milliliters of 0.100 molar sodium hydroxide to 25 milliliters of HCl, what is the pH of the solution? So again, we have a neutralization reaction, but in this case, limiting reagent will be HCl. We have 35 milliliters of 0.1 molar sodium hydroxide, 25 milliliters 0.1 molar HCl. So we have 3.5 millimole sodium hydroxide and 2.5 millimole HCl. We will deplete the HCl in this case. So this is our limiting reagent. We will deplete sodium hydroxide but we will not finish the all sodium hydroxide, and at the end we will have 1.0 millimole sodium hydroxide, and we don't have the HCl, and we created of course 2.5 millimole sodium chloride and 2.5 millimole water. And sodium hydroxide is a strong base, right? And it completely ionizes and creates OH minus ions. So we have 1 millimole, and total volume is right now is 25 plus 35. Why this is important? It is important since we have to calculate the molarity of the solution in the Erlenmeyer flask. At the beginning we have 25 milliliter of HCl, but we added 35 milliliter of sodium hydroxide, so we changed the volume. This is important since this sodium hydroxide will this sodium hydroxide will ionize, right? Completely ionize. We will create OH minus ions, but we know that during the pH or the pOH calculation we will need to use concentration. So as you know, we can calculate the pOH by minus log of the OH minus ion concentration. So OH ion concentration here 1 millimole over 60 milliliter. Since 25 plus 35 is equals to 60 milliliter. So this is molarity of the OH minus ion concentration. And we can calculate the sodium 1 over 60, and it is equal to 0.01667. And the pOH will be equal to minus log 0.01667, and it is equal to minus log 178. This is pOH. As you know from previous lesson, you know that pH plus pOH equals to 14. So if the pOH is 1.87, the pH will be equal to 12.22. So pH of the solution is 12.22. Then I want to talk about weak acid and strong base titration. It is a little bit more complicated, and I want to give a simple example. For instance, weak acid is acetic acid, CH3COOH, and we have again a strong base, which is sodium hydroxide. These two things will react with each other in aqueous phase. So this is a one-way reaction, and we will create CH3COO sodium plus water, and this is soluble. And the other thing is that acetic acid can react with the OH minus ions, and it will create CH3COO minus plus water. So here is the for instance, we have a sodium hydroxide on a burette, and we are adding on acetic acid. So acetic acid is the analyte and sodium hydroxide is titrant, and this is the analyte. So this is the system. Again, to keep it simple, sodium hydroxide concentration is 0.1 molar, and we have 0.1 molar of acetic acid and 25 milliliter. I want to make them smaller. And as you know, acetic acid is weak acid. It's a weak acid and it ionizes in water. And it creates CH3COO minus plus CH3O plus ions. And also acetate CH3COO minus ions can react with water. So this thing can react with water and can create acetic acid plus OH minus ions. So it's a equilibrium reaction. But to calculate the pH, we will need to know the Ka value of the acetic acid. So we have to know the Ka value of the acetic acid for this reaction. And also we may calculate the Kb value for this reaction. Well, since Ka times Kb equals to Kw 10 to minus 14 at room temperature. So we will need to use this information for the next parts. And we can calculate, for instance, this again, calculate the pH in the titration of 25 milliliter of 0.1 molar acetic acid by sodium hydroxide. Again, acetic acid is the titrant, it is in the Erlenmeyer flask. We have 25 milliliter of acetic acid. And we are adding sodium hydroxide from the top. Their concentrations are same. So we have 0.1 molar acetic acid concentration, and sodium hydroxide concentration is also same. So we will calculate the pH after adding 10 milliliter of sodium hydroxide solution. And to calculate it, we have to know the reaction of acetic acid and sodium hydroxide. They will react with each other and it will create this molecule and water, right? So again, I have to calculate the mole of the both of the chemicals. For sodium hydroxide, it is 10 milliliter times 0.1, which will be equal to 1 millimole. And acetic acid will be equal to 25 milliliter times 0.1 molar, which will be equal to 2.5 millimole. So definitely sodium hydroxide is our limiting reagent. And we will deplete it. and we will create acetate and water. And total volume became 25 milliliters plus 10 milliliters. So total volume is 35 milliliters. Keep it. You have to remember it. So we created 1 millimole sodium acetate. We have 1.5 millimole acetic acid. So acetic acid, we have still acetic acid in the solution, will ionize and create acetate and hydrogen plus, right? So we have 1.5 millimole acetic acid and 1.0 millimole acetate, and acetate is just coming here. So this will be ionized as CH3COO minus plus sodium plus, so we will have acetate at the end. So we have converted to the molarity, and it is actually a back and forth reaction. So we don't have hydrogen plus here at the beginning, so I am just making an ice table, right? So this thing will decrease a little bit, this will increase a little bit, and this increase a little bit. But instead of using the axis, there's an easier way here. Since we know the Ka value, and the Ka value for this reaction is 1.8 times 10 to the minus 5, and I can calculate the Ka, since it is hydrogen plus concentration times CH3COO minus concentration over the acetic acid. And this is equals to Ka, and the Ka equals to 1.8 times 10 to minus 5. So I don't know the hydrogen plus concentration, but I know the others. So 1.0 millimole over total volume, which is 35 milliliter, and 1.5 millimole over 35 milliliter. So these two are same for just a log, and hydrogen plus concentration is 1.8 times 10 to minus 5 times 1.5, and I can easily calculate this volume. And it is 2.7 times 10 to the minus 5. And the pH is equal to minus log hydrogen plus concentration. So it is minus log 2.7 times 10 to the minus 5 minus log 2.7 times 10 to the minus 5, and it is 4.57. I will use 3 significant figures. So this is our pH. So we made the A. So this was A. So here it is 4.57. For B, we have 5 milliliter of sodium hydroxide and 25 milliliter of the acetic acid. So again, there's a neutralization reaction. and we have 2.5 millimole acetic acid and 2.5 millimole sodium hydroxide. I assume that you understood the millimole calculation. I'm just multiply volume times the molarity and it becomes millimole. That's all. So we will deplete both of them. There is no limiting reagent. And we will create the acetate and water. So we have acetate and water. So this acetate ion in water can create the acetic acid. It ionizes in water and reacts with water again. So we will have acetic acid plus OH minus ions. So in this case, we need to calculate the Kb since we are creating the OH here. So we have 2.5 millimole of the acetate and the total volume is 50 milliliters, and this is equal to 0.050 molar. So I will clean here. We know the molarity. And Kb for this reaction is 5.6 times 10 to the minus 10. But again, we can calculate this value by just using this equation. If we know the Kw, which is 10 to minus 14, we know the Ka 1.8 times 10 to minus 5, so that we can calculate the Kb. And this is the Kb value. I just want to give it here. Oh, this is our Kb value. And it became a weak acid base question. So this thing will ionize and we will create acetic acid and the OH ions. And the Kb will be equal CH3COOH times OH minus ions over acetate ion. And we know that these two are just X. So X times X will be equal to X square. And this acetate ion concentration is equal to 0.050 minus X, and Kb is here, so it is 5.6 times 10 to minus 10. And we can make the calculation. So X squared will be equal to 5.6 times 10 to minus 10, 0.05 minus X, and X squared will be equal to plus, I will send it here, plus 5.6 times 10 to minus 10 X minus 0.05 times again this number. So I can just neglect this thing. Just neglect. It is so small. So x square will be, so this is equal to 0, will be equal to 0.05 times 5.6 times 10 to the minus 10, and x will be equal to square root of this thing. And this value is equal to 5.3 times 10 to the minus 6. But here, this is the concentration of the OH minus ions. And if you calculate the pH, if we can calculate the POH, it is minus log 5.3 times 10 to the minus 6, and it is equal to 5.28. So pH plus POH equals to 14, and we know the POH, and the pH is just 8.72. So this is 8.72. If you add 8.72 plus 5.28, it will become 14. So what if we exit the equivalent point? So we have a sodium hydroxide, but we exit the equivalence, then what will happen for the pH? So here it was 5.28, so 5.28, and I want to calculate number C. So we have CH3COOH plus sodium hydroxide. We will create the sodium acetate plus OH minus ions, but acetic acid will be depleted first. Why? Since we have 3.5 millimole of sodium hydroxide, but we have only 2.5 millimole of acetic acid. So this is our limiting reagent. So we will deplete the acetic acid. And acetic acid finished. We have sodium hydroxide 1.0 millimole. We have a little bit of acetate and OH minus ions. Again, there will be a reaction between the CH3 minus plus water. We can consider this reaction. So we will create acetic acid and OH minus. We can consider this reaction, but again we have to use the Kb value, not the Ka value, since we created the OH here. So Kb was 5.6 times 10 to the minus 10. So we have a acetate 2.5 millimole, and the total volume here is 60 milliliter. 35 plus 25, right? It is 60 milliliter. So I will divide this number to go back to the molarity. Zero 0.0417. And I will delete here. And we know that we have OH, which comes from here at the beginning. So it is the exact effect. So we have OH minus ions 2.5 millimole over the 60 milliliter. So it is exactly the same 0.0417 molar. So the equilibrium go to the right, since we don't have the acetic acid here, right? So minus x plus x plus x. The important thing here is that x is actually very small. It's incredibly small, and I wanted to show that. So 0.0417 plus x. So we have x here. So if we write the KB, it will be something like that. So definitely these x's will be very small. I think we can neglect them. And this x will be around 10 to minus 8. But we have already very high molarity. So we can add these two numbers together, but it will not make a change. So this part of the calculations was actually unnecessary. So we can directly calculate the POH from here, but I just wanted to show you the logic behind the reactions. So POH is minus log 0.047, and the POH probably will be equal to a pretty small number. 1.38. So pH will be equal to 12.22. So this is the pH of the solution. So what is happening is that if you start to add sodium hydroxide, the pH started to rise, right? At 10 milliliter, pH becomes 4.5. At equivalence point, it becomes 5.28, which is very different from the first one. Since if you make the strong base titration at equivalence point, the pH become 7, but in weak acid strong base titration, pH became 5.3, and if we add more sodium hydroxide, then the pH becomes 12.2. And there is only there is also other case, strong acid and weak base titration. So it is very similar, and we can choose HCl as a strong acid and weak base can be ammonia. So ammonia is the weak base, and we have to know the reactions. HCl can react with the ammonia and it will create NH4Cl. So this is a neutralization reaction, acid-base reaction definitely. But we have to know other reactions also. So hydrogen plus can, for instance, react with the ammonia and create NH4 plus, and NH4Cl can also ionize in water. So keep it in mind. So this is also another possibility. Or we can write this reaction NH4 Cl plus water is liquid, NH3 aqua plus H3O plus, and NH4 plus in aqua can create, oh by the way this is an equilibrium reaction of course, can create NH3 plus hydrogen plus ions in water, and again it's a weak base. So what we have here, we have a bread again, and we have a Erlenmeyer flask. In bread we have HCl, and in Erlenmeyer flask we have ammonia. So again we have 0.1 molar ammonia and 0.1 molar HCl, and ammonia is 25 milliliter. So if we draw the titration curve, we expect to see something like that. So we will start around 11, and when we start to add hydrochloric acid, it will start to drop, and the pH will be small if we add more. So at 25 we have an equivalence point. This is the volume of the HCl. This is volume of HCl by milliliter, and this is the pH. So we will need to use the Kb value of the NH3. So calculate the pH in the titration of 25 milliliter of 0.1 molar ammonium by hydrochloric acid after addition to the acid solution of 10 milliliter of 0.1 molar HCl. It is very similar. We have a NH3 solution and it will react with the HCl. So we will create NH4 plus ions plus Cl minus. So we can make millimole. So 0.5 times 25, it is 2.5 millimole. HCl is 1 millimole, which is 10 times 0.1 molar, so that it is 0.1 mole, then 1.0 millimole. So here HCl is the limiting reagent, so it will completely gone. We will create NH4 plus and Cl minus. So at the end we will have 1.5 millimole of ammonia, 0 HCl, 1.0 millimole NH4 plus and 1.0 millimole Cl minus ions. So we can write the Kb. By the way, Kb for this reaction is 1.77 times 10 to the minus 5. This is Kb of the NH3. Okay, this is NH3. So we have NH3 and NH4 plus. So I will consider this reaction. It's an equilibrium reaction. And Kb of this reaction is this. So we have 1.5 over, what is the total volume? Total volume is 35 milliliter. And 1.5 over 35 milliliter will give me a molarity. And we can calculate this value. 0.0428. Maybe I can use 9 here, right? So this is molarity of NH3. And I can calculate the NH4 plus, which is 1 millimole over 35, and OH is unknown. So 1 millimole over 35 is 0.286. So Kb, you know the Kb, 177 times 10 to minus 5. We don't know the OH. We know this value and NH3. And if you make the calculation, so X will become 2.66 times 10 to the minus 5. So this is the OH. And we can calculate the POH. Two 2.66 times 10 to the minus 5. And it will be equal to minus log 2.66 times 10 to the minus 5. It is equal to 4.5, 7 or 8, I think 8. So this is POH. The pH will be 9.42. This is the pH, right? 14 minus 4.58. So here pH is 9.42. So we can continue what will be in the equivalent point. So we will add 25 milliliter of HCl and we will have 25 milliliter of the ammonia. So we have a reaction. So we have 0.1 times 25, 2.5 millimole. Ammonia, we have 2.5 millimole of HCl. So both of them will be depleted. We will create these two. So we don't have HCl and ammonia, but we have NH4 plus, and NH4 plus can create the ammonia but we have to calculate the molarity. So total volume is 50 milliliter. So I have to divide this volume to 50 milliliter to go to the molarity. And if I divide it, it will basically become 0.05 molar. So I will clean here. I know the molarity. I can make the calculation from my head. So it ionizes minus X. We can create ammonia and other X, but we need to calculate the Ka. So what is Ka? Ka will be equal to Kw over Kb. I gave you the Kb value, which was what was the Kb? Kb here, 1.77 times 10 to minus 5. And we know the Kw, which is 10 to the minus 14 from the acid-base chemistry. So Ka value will be, what will be, 10 to the minus 14 over 1.77 times 10 to the minus 5. So it is Ka of this reaction is 5.65 times 10 to the minus 10. So this part was important. So if I write the Kb, it will be equal to NH3 times H plus, which will be X square, and NH4 plus concentration, and it is equal to 5.65 times 10 to the minus 10. So here we can neglect X since it is very small, and X square will be equal to times 0.05 square root of this number, and it will be 5.31 times 10 to the minus 6. So we can calculate the pH since we know the hydrogen concentration. X was the hydrogen concentration, hydrogen plus concentration, 5.31 times 10 to the minus 6, and this is equal to 5.27. So here it is 5.27. So our pH decreases as we expect since we are dropping an acid. And see what if we add 35 milliliter of HCl. So So here total volume is 60 milliliter. So there is a acid-base reaction. We have HCl plus NH3. They will both react. So we have 3.5 millimole of HCl. We have 2.5 millimole ammonia. So ammonia here is the limiting reagent. We will create NH4 and chlorine. So NH4 can ionize in water and create NH3. So Kf for this reaction, as we calculated, is 5.65 times 10 to the minus 10. However, calculating this again, like the acetic acid solution, it will be unnecessary. Why? Since we have 2.5 and we have a hydrogen plus concentration, and this reaction will try to go here. It's an equilibrium reaction, right? It is a back and forth. There are back and forth reactions. So if we write minus x plus x at the beginning, we don't have ammonia here anymore. So what will be? Ka will be equal to x times x plus 1 over 60 actually. So we 1 over 60, since the total volume is 60, we use the millimole, over 2.5 minus x. 2.5 over 60 minus x, 5.65 times 10 to the minus 10. We can say that x is very small number. Right? We don't have to calculate. So that we can say that pH is equal to 1 millimole hydrogen plus concentration over the 60. So we have to convert it to the molarity. Zero 0.01667. So we can calculate the pH, which is minus log 0.0167 and it is equal to 1.78. So pH dropped a lot. 1.78. And this is all about the acid-base titration calculations. I hope this video was beneficial for you. If you have questions, you can write comment. I read the comments and I will answer your questions. If you like the video, you can like and you can subscribe for the next videos. And thank you.